pages of this packet together, and then you guys will have time to work on the last 2 pages, you know, in partners or groups if you'd like. And then I'll collect it at the end of class. So the first page is focusing on earthquake waves. Remember, we have 4 types of earthquake waves. We have 2 that are what we call body waves, and our body waves are traveling through Earth's interior. They're traveling through the body of Earth. And we have P waves, which are primary waves. Remember, our primary waves can travel through solids, liquids, and gases. And then the other type of body wave is S waves or RS waves, or those are called secondary waves. And secondary waves cannot travel through liquids or gases. S waves can only travel through solids. And then we also have Love and Riley waves. Those are our surface waves. And our surface waves are the ones that travel on the surface. And when we see those on a seismograph like we have down here at the bottom of this worksheet, we plot our surface waves together. So in a second, when we're looking at indicating what waves are on our seismograph, know that we have P waves, S waves. We have our 2 body waves arrive separately. And then we have our surface waves that kind of arrive all together, and we can't pick them apart. Remember that primary waves, P waves, travel fast. They're the fastest. And then secondary waves are the second fastest. Right, primary, secondary, first, and second. All right, so first we're going to label the layers of the Earth. So out here, this line, this is off again. Hold on. The calibration on this thing gets off, and then where I draw, it doesn't actually put stuff. All right, so this line here is the crust. And then this layer is the mantle. And then we have the outer core and the inner core. Right, so we are depicting the Earth's interior, and we're going to draw the body waves moving away from this earthquake, right, marked by the star, the focus of this earthquake, towards each one of our houses. And remember, the body waves in the Earth's interior get deflected due to just the way that Earth's interior, the material has formed. They get deflected a little bit, like so how they don't move in a straight line, just like when you put a straw in water and it gets deflected, right? And it looks funny when your straw, you know, or like your leg in the pool looks funny, like it's not connected to your body, right? It looks bent. Same thing happens to earthquake waves in the interior of Earth. So they get a little curvature. So we're going to draw our body waves from our earthquake to house A. It's basically a straight little path with a little bit of a curve in it. And then we can draw, again, to B, similarly, basically a straight line. It's got a little bit of deflection in it as it moves through the mantle. Same thing for C. Notice that A, B, and C are all just moving through the mantle. Okay, so they are this essentially straight path with a little bit of deflection due to what the mantle is composed of. But as we draw our line to D, Those waves are going to have to move through the outer core. The outer core is made up of different material than the mantle. And so what happens is we start going on our straight path. We hit the boundary of the outer core. We're going to continue on that straight path, but it gets a little deflected. And then as we move through the mantle, we have another little deflection. So next, we're supposed to label the segments of each path with the type of body wave that's found on that segment. So whether it's P, S, or P and S. So remember, primary or P waves can travel through solids and liquids. S waves can only travel through solids. So in our mantle, remember our mantle is a solid. So we should have P and S waves traveling through our mantle. So for A, we get P and S, right? Because it's only traveling through the solid mantle. Same thing for B. We have our P and S waves because the mantle is solid. And then same thing for C. We have our P and S waves because they're traveling only through that solid mantle. The weird one is D, where we start out from our earthquake and we're traveling through the mantle, and so we have P and S waves traveling through the mantle. And then we hit the outer core. The outer core is a solid, a liquid, or a gas? Liquid, so we have a liquid outer core. So if we have a liquid there, what type of waves are we going to have? P, yep, primary waves. No secondary waves, right? Because they get stopped, they can't travel through the liquid. Right, they're done. And then our S waves don't pick up on the other side. They are just gone. So this segment is also only P waves. All right, so then the next part is to determine which of our seismographs are related to each house. And this is like a picture, so you can't see the colors as well. But on yours, you can see that you have like a medium gray, a dark gray, and a light gray down there for your 3 different wave types. And so remember, the closer you are to an earthquake, the closer together all of those waves are going to happen. So which one of these is house A? The second one. Good job. And then what about house B? The first one. And then C is the last one, which leaves D as this one. And then the last thing we need to do on our seismographs is label the type of wave that's arriving in our record. So that's where those different colors come into play. So all of our medium gray ones, all of our very first waves are going to be which PS or surface. P waves, right? Primary, first ones to get there. The second one is going to be our S waves. And then the last one's going to be surface. Notice that the surface waves are usually much higher amplitude. Right? They're a little crazy, more wiggly. Then A, they're all super close together, right? Because it's super close to the earthquake focus. What about for D? What's this one? Yeah, there's your P, and then what's this one? Surface. You got it. Right? No S wave, because our S waves don't get there because they go through liquid and they get stopped in the liquid. And then for the last one, P, S, and surface. Sweet. Bless you. Okay, so for volcanoes, I want you to remember viscosity. Which is resistance of a fluid to flow. And so, for example, a low viscosity fluid would be maybe water. It's very flowy, not very sticky, right? Very runny. But a high viscosity fluid might be syrup, molasses, oil. Anything that flows a little more slowly would have a higher viscosity. Right, so remember, viscosity is just that fancy word that means how runny or sticky or thick it is. So when we're talking about volcanoes, we have, again, different volcano types, and those different volcano types are related to different types of eruptions, and eruption types are related to the composition of the lava, right? So what the lava is made up of. And we have two main types of lava. We have felsic lava, which has lots of silicon and oxygen chains. And when it has lots of silica chains, then you have these really, really long chains of molecules, and they get all stuck together, right? And so if they get all stuck together, that's a very sticky lava, right? Because you have these big, long chains. Think of just like a chain of, like a metal chain, right? That's like getting all tangled up in itself. It's not very easy to pour that out. And then mafic lava doesn't have so much silica. It has more iron and magnesium, which actually breaks up those chains. And so our mafic lava is going to be more like, you can think of it as macaroni, right? If we want to compare our chains like spaghetti to macaroni. Felsic and mafic are just fancy geology words to talk about whether it has more silica or more iron and magnesium. My favorite joke is about felsic and mafic is, why didn't the granite come to school today? Because he fell sick. All right, so felsic or mafic, which one would be runny? The one that's made up of spaghetti or the one that's made up of macaroni? Macaroni, right? Macaroni is easier to pour. So our macaroni one is mafic, which means that felsic, the spaghetti chain, lots of silica chains, lava is more viscous. And then down here at the bottom, we have two profiles of a volcano. So remember, profile, just like the side of your face is called your profile, right? The side of a volcano is its profile. And so if we look at the sides of volcanoes, we can get some clues about the type of lava that they're formed from, whether they're formed from runny or viscous lava. So on the diagram below, right, runny next to the volcano that formed from runny lava, and viscous next to the volcano that formed from viscous lava. So which one of these formed from flowy, runny lava? The one that lava spreads out a bunch, or the one where it's all stuck in one place? What? Deposit?
Composite.
Composite is running lava or viscous lava?
Run.
So if you have running lava, it's gonna like, if you pour a glass of water out, it's gonna like flow really far out on the table, right? So that would be shield. If you pour molasses out on the table in January, when it's super cold, right? You're gonna get more of a composite situation happening. All right, so, and then on the diagram, we should write mafic next to the one that's formed from mafic lava and felsic next to the one that's formed from felsic lava. So up at the top, we know which lava is runny. Mafic lava is runny, so next to the runny one, we'll write mafic. And felsic lava is viscous, so we'll write felsic next to the felsic volcano. And then we have two different igneous rocks associated with these volcanoes. We have rhyolite, which is formed from felsic lava, and basalt, which is formed from mafic lava. So felsic is going to be our rhyolitic. Volcano, and our shield volcano is going to be made of basalt. All right, so far our shield volcano is runny, mafic, basaltic lava, and our composite volcano is viscous, felsic, rhyolitic, or rhyolite lava. So volcanoes can or will erupt explosively if gases cannot easily escape. Runnier lava lets gas bubbles out peacefully, so there's no explosion. So which lava lets out gases easily? The running one, which is mafic. All right, so then we'll write explosive next to the one that erupts explosively and peaceful next to the one that erupts peacefully. If mafic lava lets gases escape easily, then it is peaceful. Yep. And composite volcanoes with viscous lavas have explosive eruptions. And then you can actually go ahead and do the rest of this one by yourself. Explain which type you would like to live next to and why. But before I let you go completely, on the next volcano worksheet, it talks about hotspots. And I actually didn't talk about that in lecture, but I want to just explain it to you really quickly. So hotspot volcanism is just volcanoes not associated with plate tectonics or plate boundaries. So remember, when we were talking about volcanoes and earthquakes, the vast majority of our volcanoes and earthquakes occur at plate boundaries, right? So we use the evidence of the location of volcanoes and the location of earthquakes to come up with the theory of plate tectonics, right? That's one of the biggest supporting factors for the hypothesis of seafloor spreading and the theory of plate tectonics. But there are some volcanoes on Earth that are not associated with plate boundaries, and those are called hotspot volcanoes. And in hotspot volcanoes, what we actually have going on is that if we look at sort of like a cross section, this is the surface of Earth. We get really these kind of like hot spots in the mantle, right? They're called hot spots. They're called mantle plumes. So they're this part of the mantle where it's hot and it kind of wells up towards the surface. And so you get this little, like, you can almost think of it like kind of a burner, right? Close to the surface of the Earth, where it's a little warmer than the rest of the mantle that surrounds it. And it's warm enough to create volcanoes up here on the surface of Earth. Right, so we can make our volcanoes above our hot spots. But what's going on is our mantle plume is really deeply rooted and it doesn't move around. So it just stays there. Think of it like a burner on your stove. And then you have the plate of lithosphere, right? The plate moving on top of it. And that plate is moving because of plate tectonics, right? And so it's going to move over that hot spot. And we get something called time transgressive volcanism, where you get usually like chains of volcanoes, right? So Hawaii is a really good example of hotspot volcanism, where we have this hotspot. Hawaii is literally in the middle of the Pacific plate, right? Not associated with any plate boundaries, but it's moving over this hotspot and we get those volcanoes there. Yellowstone is also a really good example of a hotspot, where like Yellowstone used to be farther west, right? Our plate has moved Yellowstone, the hot spot, right? The volcanism of Yellowstone to where it is today. So that's what hotspot volcanism is. I didn't talk about it in lecture, and then this little paper talks about it. So go ahead and work on these worksheets. I'm here to help. You can work together. And then you can, whenever you're done, you can turn it in. And then you're done for the day.